Good afternoon, everyone, and welcome to the 13th edition of our INFOGEST Viva Webinar. My name is Ever Hernandez, and I would like to introduce Shannon Gwala, who will conduct the webinar with me. This event is organized by a team of postdocs from Chagas Food Research Center in Ireland. These webinars are aimed to share the latest findings in digestion with presentation from the most recently graduated PhD, postdoc, and young researchers. This webinar is broadcasted live on YouTube and will be accessible in our InfoGest YouTube channel. The presentation, in this time in a pre-recorded video, will be followed by a question and answer session with the speaker. So I actively invite you to use the Q&A button at the bottom of your screen to ask your question. Our speaker today is Vera Cebrián Lloret. Vera holds a degree in food science and technology from the Polytechnic University of Valencia in Spain. Currently, she is in the final stage of her doctoral thesis, which she is conducting at the Institute of Agrochemistry and Food Technology. The title of her thesis is Valorization of Marine Biomass for Development of Biopolymeric Materials and Additives with Functional Properties. Through her PhD thesis, Vera has explored the potential of different seaweeds and their industrial residues to generate bio-based materials for food applications, gelling additives, and she also has explored the digestibility of different seaweeds and their processed products by applying the InfoGest method. So, Vera, the floor is yours.
Hi, good afternoon. My name is Vera Cebrián, and I am here to present my doctoral thesis, which I am currently conducting at the Institute of Agrochemistry and Food Technology, and is entitled Valorization of Marine Biomass for the Development of Biopolymeric Materials and Additives with Functional Properties. Today, society faces a critical challenge that puts the sustainability of the planet at risk: the scarcity of resources and climate change. The exponential growth of the world's population and the overexploitation of finite resources have triggered an unprecedented environmental crisis, where pollution, food scarcity, and global warming are just some of the many challenges we must confront to ensure a viable future for next generations. One of the main concerns arising from this situation is the massive accumulation of plastics in natural ecosystems. Plastic production has experienced a significant increase in recent decades, currently reaching around 350 million tons per year. Moreover, due to the non-biodegradable nature of conventional plastics, the management of generated waste has become a major issue, especially considering that millions of tons of plastic waste end up in the oceans, impacting marine life and ultimately humans by entering in the food chain. In this context, the concept of circular economy emerges as a promising alternative to address these challenges. The main principle of this economic model is to reduce, reuse, recycle, and regenerate resources instead of merely extracting, using, and discarding them. This is intended to minimize waste generation and pollution while promoting efficiency in the use of natural resources. In this regard, one of the most promising solutions to address plastic pollution is the replacement of conventional plastic materials with biodegradable polymers obtained from natural resources. Along these lines, the trend towards reducing the processing of raw materials as much as possible to generate the final products, like a minimal processing, is also attracting attention in the search for sustainable production strategies. The central premise is to take advantage of resources in their most natural state and minimize the generation of byproducts and waste, promoting a cleaner and more efficient production. In addition to changing the way materials are produced, it is also crucial to explore new food sources, as agriculture is ultimately responsible for approximately 40% of all greenhouse gas emissions, significantly contributing to global warming. Climate change is also severely impacting on water and arable land availability. On the other hand, dietary habits have been changing over the last few years. Society is more and more aware of the impact of food on health, and there has been a significant growth in vegetarian and vegan markets. This also reflects an increased willingness among consumers to adjust their habits in response to climate change, opting for plant-based food instead of animal alternatives. In the context of exploring alternative biomass sources for the production of both biopolymeric materials and new foods, marine resources such as seaweeds have emerged as an interesting and sustainable alternative to terrestrial biomass. Seaweeds are classified into three main groups: brown, green, and red seaweeds. Although both their composition and the structure of their cell walls vary significantly depending on the species, in general, many of them contain a significant amount of compounds of interest, such as proteins, minerals, vitamins, and other bioactive compounds, as well as structural polysaccharides like cellulose and phycocolloids. Phycocolloids are a group of natural polysaccharides found in the cell walls of certain species of seaweeds. They are known for their ability to form gels and colloids when in contact with water, making them valuable in various food applications. The most industrially relevant phycocolloids obtained from seaweeds are alginate, which is present in the cell wall of some brown seaweed species and is composed of units of manuronic and gluuronic acid; agar, which is present in the cell walls of some red seaweed species and is composed of two main fractions: agarose, which is responsible for its sealing capacity, and agaropectin. And finally, carrageenans, which are also present in red seaweeds. There are several types of carrageenans, but the most common ones are kappa, iota, and lambda. As a result, seaweeds have gained significant commercial importance in the food industry, being globally used for purposes ranging from the industrial extraction of phycocolloids to obtaining bioactive compounds. However, yields in the industrial extraction of these compounds are often not very high, leading to substantial amounts of seaweed biomass waste, which is typically discarded. Therefore, waste derived from seaweed biomass, whether of natural or industrial origin, emerges as a more environmentally sustainable option to produce both biopolymers and active compounds for food applications, aligning with the principles of a circular economy. Consequently, the general objective of this doctoral thesis was the valorization of marine biomass for the development of biopolymeric materials and ingredients for diverse food applications. To achieve this general objective, three specific objectives were proposed. The first one was to valorize the biomass of various seaweed species to identify compounds of interest and evaluate their potential for producing biopolymeric materials and protein-rich food ingredients. The second one was to examine various seaweed species for efficient agar extraction using simplified methods and evaluate the suitability of the obtained agar-based extracts to develop hydrogen-like extractors and biofilm for food applications. And finally, the last one was to valorize industrial waste derived from alginate processing to obtain cellulose-based fractions using simplified methods, and then evaluate their potential for biopolymeric material production. The objectives were materialized in 6 individual case studies, which have been structured in 3 chapters in this thesis. But because of time, today I'm just going to go deeper in 4 of these studies. The first chapter is entitled Valorization of whole macroalgae biomass for food-related applications and includes 3 different works. As I previously mentioned, I'm not going to go deeper with this work, but I just want you to know that in this study we focus on analyzing the biomass composition of the macroalgae Rugulopteris, which is a fast proliferation invasive species that represents a threat to marine ecosystems. In this way, we aim to identify potential value-added compounds for different industrial sectors so that it can be transformed from a current threat into an opportunity. So let's go with the second work of this chapter. In this study, 4 different species of red seaweeds were minimally processed through a combination of melt blending and compression molding, aiming to obtain packaging materials in a more energy-efficient way. Additionally, we also wanted to investigate the impact of the composition and cell wall structure of the different seaweed species on the final performance of the films. We could observe that the seaweed biomass was mainly composed of carbohydrates, but significant amounts of proteins and ashes were also detected. Helidium corneum showed the highest cellulose content and the lowest agar content, although it was composed of almost 97% of agarose, which, as I mentioned before, is the fraction responsible for its sealing capacity. Gracilariopsis longissima presented a higher cellulose content and a lower agar content, with almost 26% of it constituted by agaropectin. Agarophyton chilensis and Gracilaria tenuistivitata exhibit very similar cellulose and protein contents, but differ significantly in their agar concentration. Agarophyton chilensis was the species with the highest agar content, although its agaropectin fraction was also quite high. Gracilaria tenuistivitata showed a lower agar content but consisted of almost 93% of agarose. As we were going to use the melt mixing technique to produce the films, we wanted to check the optimal processing conditions. To do so, we focused on one of the parameters that we consider to be crucial, the processing temperature. So what we did was to subject aqueous dispersions of the seaweeds to a range of temperatures up to 130 degrees, and then we analyzed them by means of small-angle X-ray scattering and optical microscopy, where we could observe that the greater cellulose content in Helidium corneum limited the diffusion of agar when the seaweed aqueous suspension were processed at high temperatures. In contrast, the more amorphous character of the agar in Agarophyton chilensis and Gracilariopsis longissima promoted its diffusion towards the liquid medium. In any case, increasing the temperature to 130 degrees seems to promote a greater release of agar. When producing the films, the cellulose content seemed to be the main factor controlling their mechanical and water barrier performance. The higher cellulose content of Helidium corneum resulted in stronger films with high water vapor barrier capacity, while the higher agar content of Agarophyton chilensis improved its elongation capacity. The films made from Gracilariopsis longissima also show interesting properties due to the relatively high cellulose content, offering an interesting alternative to produce biopolymeric films. So, the results from this work evidence the potential of red seaweed biomass to generate food packaging materials in a cost-effective and environmentally friendly way. After studying the composition of this red seaweed species and noticing the relatively high protein content, the idea emerged that, in addition to the production of biopolymeric materials, they could be also used as food sources for human consumption. This is why, in the third study from this chapter, we evaluated the nutritional quality and digestibility of the proteins present in two of the previously studied red seaweed species, Helidium corneum and Gracilariopsis longissima, through in vitro gastrointestinal digestions applying a method based on the INFOGEST protocol. Additionally, we also wanted to investigate the impact on their digestibility of the seaweed's cell wall structure and composition, as well as the effect of two different processing methods which could be used to generate seaweed-based snack foods, which are the extrusion and the extrusion with a subsequent compression molding to obtain biofilms. This work was carried out in collaboration with the Food Proteins Group at the Institute of Food Science Research. The in vitro gastrointestinal digestions were performed following the INFOGEST protocol with some specific modifications to make it suitable for seaweeds. After the digestions were complete, we proceed to separate the absorbable fraction from the non-absorbable fraction through selective precipitation with methanol. These digestions were also carried out using a nitrogen-free blank, which consisted of a protein-free cookie. With the results obtained from our samples, including the cookie, we calculate the digestibility. And to determine the nitrogen content in the supernatant pellet, we use three methods: total nitrogen bihedral, total amino acids, and total free primary amines using the UPA method. The initial protein content of both seaweed species was around 16%, being most of them entrapped within the seaweed cell walls, as we could see in the images taken under the confocal laser scanning microscopy. The application of mechanical processing, along with high temperature, can effectively permeabilize or partially disrupt the cell wall structures, resulting in the outward migration of proteins. As a result, protein seems to be more homogeneously distributed through the whole structures of the extrudates and films. Both species exhibit similar amino acid profiles. with aspartic acid, glutamic acid, glycine, and alanine being the most abundant. After processing, we could see a decrease in the relative contents of some labile amino acids, such as lysine, glutamic acid, and aspartic acid. These changes indicate that the amino acids present in the native seaweeds might have undergone chemical reactions upon processing, such as Maillard reactions, promoted by the high temperatures applied and by the presence of polysaccharides. Nevertheless, essential amino acids constitute more than 35% of the total amino acids in both the seaweeds and their processed products. The native seaweeds and their processed products were then subjected to in vitro gastrointestinal digestions. The digestibility of the different samples was then estimated using 3 different methods: total nitrogen by Heldal, quantification of total amino acids, and OPE analysis. Due to the intricate cell wall structure of the seaweeds, both species presented rather low protein digestibility values of around 49–51%. However, processing through extrusion with or without an additional compression molding step permeabilized the cell walls and promoted the release of proteins, enhancing the overall protein digestibility. Nevertheless, the differences in the composition and cell wall structure of the 2 seaweed species resulted in different behaviors. In the case of Helidium corneum, its more rigid and resistant cell wall required a greater extent of processing to be partially distorted. Accordingly, the digestibility appeared to increase with each subsequent processing step. In contrast, the thinner cell walls from Gracilariosis longissima were capable of releasing proteins and agar to a greater extent with the extrusion step, where the digestibility reached its maximum value. In that case, further processing by compression molding seemed to be detrimental for the protein digestibility, which could be attributed to a greater release of agar, forming a jelly network. Interestingly, the changes produced in the amino acid profiles of the processed products have a negative impact on the protein nutritional quality, especially in Gracilariosis longissima, where the digest values were reduced to levels similar to those of Helidium corneum. This means that even though the overall digestibility of the seaweed increases after processing, the amino acid profile is negatively impacted from a nutritional perspective, which is probably due to the degradation of labile amino acids such as lysine, which became the limiting amino acid. So, to improve the protein digestibility while preserving the nutritional quality, other processing techniques which do not induce amino acid chemical reactions should be tested. Moreover, the processed products could be complemented with other protein sources rich in lysine to improve their nutritional quality. But in general, we think that these results provide a basis for the development of strategies to improve the nutritional quality of proteins from Helidium corneum and Gracilariosis longissima to produce high-quality food products, thereby opening the way for potential applications in the food industry. In the second chapter, which is entitled Valorization of phycocolloids extracted from macroalgae biomass, various seaweed species were investigated to efficiently extract agar through simplified methods and evaluate the suitability of the agar-based extracts for developing hydrogel-like structures and biofilms for food applications. Of the first work of this chapter, I just want you to know that we evaluated the ability of 2 agar-based extracts with different degrees of purity obtained from Helidium corneum to form packaging films through a combination of melt blending and compression molding. Additionally, we also investigated the stability of these films during storage. It is a published paper, so if you want to know more, you can check it on the internet. So let's go with the second study. In order to investigate new sources for obtaining high-quality agar, in this study we conducted a comparison of the composition and gel-forming behavior of agar fractions obtained from different red seaweed species through 2 different methods. One of these methods was a conventional extraction process similar to the one used in the agar extraction industry, while the other was a more energy-efficient extraction protocol. These methods were applied to various species of red seaweeds, including Helidium corneum and 2 species from the Gracilaria genera, Agarophyton chilensis and Gracilariopsis longissima. Additionally, we also assess the suitability of these agar fractions for their use in the food industry. The results of this study showed that, despite a significant decrease in the extraction yield, the application of a conventional alkaline purification pretreatment to remove impurities was effective in producing extracts with higher carbohydrate content without affecting the agarose-agaropectin ratio. Consequently, we generated hydrogels with greater firmness and strength. Surprisingly, the presence of agaropectin with a semicrystalline structure and lower sulfation degree in the agar fractions of Gracilaria species, especially Gracilariopsis longissima, promoted the formation of more densely packed hydrogel networks with superior mechanical properties and higher gelation temperatures than those observed in the purified fraction of Helidium corneum. On the other hand, the simplified extraction protocol produced less purified agar fractions that contained additional compounds such as proteins, polyphenols, and minerals. The hydrogels produced with these less purified fractions exhibit less rigid behavior within the linear elastic region and lower resistance to fracture during compression compared to the more purified ones. Nevertheless, the less purified agar fractions could be viable in the production of hydrogels with bioactive properties, used as texture modifiers in specific applications within the food industry. This study also highlights the potential of Gracilariopsis longissima as a cost-effective alternative to the more commonly used Helidium corneum for the production of agar hydrogel for food application. And finally, the third chapter of this thesis, which is entitled Valorization of Industrial Residues Derived from Phycocolloid Extractions, and consists in just one work. And the aim of this work was to valorize the industrial byproducts generated after alginate extraction to obtain cellulose fractions through simplified methods and assess their potential in the production of biopolymeric materials. To this purpose, we used the waste from the extraction of alginate from 3 brown seaweed species, Alaria esculenta, Saccharina latissima, and Ascophyllum nodosum. When we characterized the samples, we could see that the native seaweed biomass consisted of up to 55% of carbohydrates, along with significant amounts of other compounds such as proteins and minerals. After alginate extraction, a significant reduction in mineral content was observed, while both protein and polyphenol content were concentrated in the residues, increasing their antioxidant potential. Carbohydrate content, on the other hand, was not significantly affected. In this regard, a small amount of residual alginate was identified in the residues. Furthermore, when delving into the carbohydrate composition of these residues, it was found that Alaria and Saccharina residues were notably enriched in cellulose, whereas Ascophyllum residues exhibit a higher concentration of fucoidan. This suggests that while Alaria and Saccharina residues are suitable for obtaining cellulose fractions, Ascophyllum residue may hold promising potential for the extraction of fucoidan-rich fractions. Then, we produce a range of cellulosic fractions with different purification degrees. Specifically, the F2A fractions obtained by applying a chloride treatment to remove lignin, pigments, and some non-cellulosic carbohydrates were mainly composed of cellulose and residual alginate, with Alaria being richer in alginate and Saccharina richer in cellulose. Conversely, the F3A fraction obtained by applying, in addition to the chloride treatment, a subsequent alkaline treatment to remove non-cellulosic carbohydrates, and the F3B fraction obtained by directly applying the alkaline treatment were almost pure cellulose, with a content exceeding 95%. These fractions were employed to produce films and their structural and functional properties were characterized, aiming to evaluate their suitability as materials for food packaging. Overall, films with higher cellulose purity, specifically F3A and F3B, exhibit more desirable characteristics in terms of visual appearance and mechanical properties. Moreover, was observed a decrease in water sensitivity and permeability in the F2A and F3B films. Therefore, the simple alkaline treatment applied in the extraction of the F3B fraction results in the production of cellulosic films from seaweed waste with an optimal balance between functional properties and consideration of economic and environmental efficiency. So, as general conclusions of this doctoral thesis, we can say that cost-effective and environmentally friendly materials for food applications can be developed from red seaweed biomass through minimal processing approaches, with the composition and structure of the seaweed cell walls playing a fundamental role in understanding how each species behaves during processing. Native seaweeds have low digestibility, which improves after processing through extrusion and compression molding. This improvement is influenced by both the composition and the structure of their cell walls, as species with taller cell walls and higher cellulose content require a higher degree of processing to enhance digestibility. However, processing negatively impacts the amino acid profile and nutritional quality of the proteins. The application of an alkaline purification process leads to the formation of hydrogels with significantly higher strength and hardness. On the other hand, the simplified extraction protocol produces less purified agar fractions that could be advantageous for the production of hydrogels with bioactive properties. Cellulose fractions with higher purity can generate films with more desirable mechanical properties and visual appearance, while the less purified fractions favor a greater water-vapor barrier. Nonetheless, the application of a simple alkaline treatment is sufficient for the production of cellulose fractions that result in films with an optimal balance between functional properties and economic and environmental efficiency. So that's all. Thank you so much for listening to me, and thank you so much for having me here in this webinar. You have my mail, so if you need something, and if you have any question, please don't hesitate to ask.
Right, Vera, congratulations on your great PhD work. You showed us some great insights from there, and now we're just going to open question and answer segment, and we invite our participants to drop in any questions that you might have for Vera. I do have some here. If you could please explain to us in more detail what kind of modifications you would have applied to the INFOGEST model in order to adapt it to your seaweeds. Can you just further explain?
Yes. The main modification we made was the way we handle with the supernant and pellet fractions, because I think that we are more accustomed to analyze the supernant in a liquid state. And in that case, in our case, both of them were in a solid state. We freeze-dried both of them. That we make this decision because of the composition of the seaweeds. The seaweeds have a significant content of fiber, and this fiber tends to absorb significant amount of liquids.
Okay.
So, yeah, so we consider that if we didn't analyze or this kind of the supernant and pellet in a dry state, we couldn't be able to compare them properly, since apart from the digestion of the proteins, the amount of methanol absorbed would be also affected.
All right, thank you for that. We have one question in the Q&A. I'll just open that. It's more or less of a comment, and they comment that it was very interesting. So
thank you so much.
Yes. Right. So you showed us the protein digestibility of spot seaweeds after processing, and we saw that it was quite low when we compare it to, for example, dairy or, for example, legumes. Would you like to comment on why this is the case for seaweeds?
Yeah, I don't think is that low compared with that kind of plant-based proteins. What we've seen is similar to beans or what I know. Maybe I'm wrong. It's obviously lower than animal-based proteins, but from some plant-based proteins are similar. But if it's lower, it's definitely due to the interactions between the polysaccharides and the proteins.
Okay, so the polysaccharides are
interacting
covalently bonded, or you think
what, please?
Are they covalently bonded, or what is it with the polysaccharides?
When we process, when we do the processing, the polysaccharides, the agar, migrates through the cell walls, okay, with the proteins, and they form like aggregates.
All right.
So this is probably what's happening with the digestibility.
Okay, thanks for that. Then you showed us also in the first part some seaweeds that you would have heated, but you didn't digest that. Would you comment that because you had the effect of processing temperature, do you think that this processing would improve or negatively affect the digestibility of the nutrients of the ones you didn't show us?
Yeah, okay. The temperature, what we've seen in this study is that processing with temperature improve digestibility, but impact negatively in the protein quality. Okay, but when we prepare the samples, we use the conditions that we used to use for the preparation of films for proof packaging. We didn't know what to expect with the proteins. So now, seeing the results, we know that this wasn't the processing conditions. So we should optimize them, trying to reduce as much as possible the temperature of processing and the time of processing, trying not to trying to avoid the detrimental of the nutritional quality.
Yeah, Vera, I really saw something that I thought was very interesting from what you've just explained, that not only is it important to talk about the digestibility, but to also look at what is happening to specific amino acids. So you might have a higher digestibility, but you have lost some through heating, which may be essential. So you show it, and that's really interesting. Thank you for that insight. So would you think that if we would purify these proteins, isolate them, so to say, would they then have a higher digestibility?
Yeah, I think so. We're now currently working on that. We are now trying to extract and purify proteins from the native seaweeds, not only from the native seaweeds, also from the waste that they are produced after the agar extraction, because we've seen that this waste contains a lot of proteins. Proteins are concentrated in that. But as I said, we are currently working on that because, as you said, we believe that this probably improve the digestibility.
Right. Thank you so much. We have another comment in the Q&A, and the attendee is just thanking us, and they are saying these presentations are helpful.
Thank you so much.
Yes. Eva, would you have a question for Vera, because I've run out now? Okay. It seems that you were very clear, and I'm sure that if someone has a question, they are going to email you for more clarification or refer to the papers and all of that. So thank you so much, Vera. So over to you, Eva. I think you have some more information for us.
Yeah, thanks, Shannon, and thanks, Vera. Thank you very much, Vera. Your presentation was really interesting, and also this discussion in the Q&A section. But now we have some announcements. So I'm sharing my screen. Let me know if you see my slides. Yeah, okay. So working now. So we are still looking for speakers for the next year. We have some slots for January, February, and March because we are doing these webinars until the next INFOGEST conference in next year in Porto, in Portugal. So if you are interested or know someone who could benefit from this opportunity, please share this information, and we will be waiting for application via email that is shown here. And also, we have some news about the INFOGEST conference on food digestion for next year conference. So the deadline for the submission of abstract for both oral and poster presentation has been extended to the 10th of January. So if you haven't submitted your abstract yet, so you still can do it. And here is the main topics of the conference. Please have a look. And I think that's it from my side. So many thanks to our speaker and to all attendees. We wish you all the best for these Christmas holidays, for this small holidays period. And that's it. See you at the next webinar in the next year. So thank you.